Production. I feel really honored to have a chance to speak in the Colloquium of KAIST. Thank you very much again for inviting me. Today we will mainly discuss small cancellation groups, such as genus 2 closed orientable surface groups, 2 bridge link groups, and even Hecoid groups. All of these are fundamental groups of 2 or 3-dimensional manifolds or bifolds. In the case of low-dimensional manifolds, many important properties are determined by the behavior of simple loops in the manifolds. From this point of view, you like to investigate their fundamental groups. And in particular, if those fundamental groups are small cancellation groups, we may apply small cancellation theory to such groups. To help your understanding better about what small cancellation theory is and how the theory can be applied, let me first show you an easy example, but interesting, concerning genus 2 closed orientable surface groups. And after that, I'm going to discuss some of my recent results about 2 bridge link groups and even Hecoid groups, which is joint work with Makoto Sakuma. Let me first show you an easy example concerning genus 2 closed orientable surface groups. In this talk, let's let G be the fundamental group of a closed orientable surface of genus 2. Then we know that the G has this presentation with 4 generators x, y, z, u, and a single relator x, y, x bar, x inverse, y inverse, and z, u, z inverse, u inverse. For convenience here, we use the notation x bar, y bar instead of x inverse, y inverse. And then suppose that we want to know whether or not the subgroup generated by x squared y g u of G is free. As a matter of fact, this subgroup is already known to be free by the covering space theory. According to the covering space theory, any subgroup of G of infinite index is free. So the subgroup in our consideration has obviously infinite index, so it must be free. But in this talk, we would like to look at a more elementary proof without using any high technology. Supposing that this subgroup is non-free, we would like to obtain a contradiction. In other words, supposing that there is a non-empty cyclically reduced word W in this set x squared y z u such that W equals the identity in group G, we would like to obtain a contradiction in 2 different ways. The first way is using universal covering space of S sub 2. In this talk, S sub 2 denotes a closed orientable surface of genus 2. And this topological proof was introduced by Gyuntae Kim, who is a student of my coworker, Makoto Sakuma. And the second way is using a small cancellation theory. And I believe the second method can help you understand how small cancellation theory can be applied in contrast with the first topological method. Now let me first show you a topological proof using universal covering space of S sub 2. First of all, we need to construct the universal covering space of S sub 2 in the Euclidean plane. This regular octagon is the canonical polygon of S sub 2, since by identifying the corresponding edges, we have S sub 2. Then to get the universal covering space of S sub 2, we need to make a tessellation with infinitely many copies of this octagon by joining 8 octagons at each vertex. But since regular octagons cannot form a tessellation in the Euclidean plane, so we use irregular octagons here. In the first step, place a regular octagon in the center here. and then join 8 octagons at each vertex by joining them to each other along the identified edge. There is a unique way in doing this, because in this octagon, there are only 2 edges to be identified, and you cannot flip this octagon over along the identified edge. There is a unique way, which means that if the label of this regular octagon is given like this, then the labels of the other edges are determined automatically. And then place all the vertices of these octagons on the same circumference, except these 8 vertices, and continue this process to fill the whole plane. That's the universal covering space of S sub 2 in the Euclidean plane. And then we fix the origin in somewhere in the regular octagon in the center, like this. Then there is a unique edge path P starting from this origin, which represents W. But since W equals the identity in the fundamental group of S sub 2, the path P should be closed. Then there is an outermost circle C which P passes through. We pay attention to such outermost circle C. And then we divide into 2 cases according as how P reaches C for the first time. Again, all of these polygons are actually octagons. But for convenience, let me call this triangle. Let me call this quadrangle. Then the first case is that this closed path P reaches the outermost circle through a triangle. And the second case is that P reaches C for the first time through a quadrangle. So let's look at case 1 first. P reaches C for the first time through a triangle, like this. Please remember that P represents W, and the W is a word in X squared, Y, G, and U, which means that wherever X occurs in W, X squared occurs. In other words, a single X or X bar cannot occur between 2 other letters. Then if P, this is a part of P, red part, then if P reaches the outermost circle through a triangle like this, then this P passes through 7 edges of this octagon. But as I said, a single X and X bar cannot occur between 2 other letters. The only possibility is this. X occurs in the left end and the X bar occurs in the right end, like this. For middle part, we have 2 possibilities, this one and this one. And after this, there are only 2 directions in which P may proceed. P may keep to this circle after this point, like this, or P may move into the inner circle, like this. Actually, there are there are 5 edges attached to this vertex. But P may not go to that direction because this is the outermost circle that P passes through. So P cannot go to the outer circle. So there are only 2 directions in which P may proceed, this direction and this direction. And in either direction, we see that a single X occurs between 2 other letters. Here we see that X occurs between G and the U bar. And here, X occurs between U bar and the Y, which is a contradiction to the fact that P represents W. And also, let's look at this case. X occurs in the left hand and X bar occurs in the right hand. And after this point, again, we have only 2 possibilities. P keeps to this circle and P goes into the inner circle, like this. If P goes into the inner circle, then we have a contradiction because here a single X occurs between Y and the Y bar. So P cannot represent word W. We have contradiction. But if P keeps to this circle, then one more x occurs consecutively, we see it. So x squared occurs here, so there's no problem with this. But here, x bar occurs between u and y bar. This gives us a contradiction. So this case is also a contradiction. And what about case 2? Case 2 is the case where P reaches C for the first time through a quadrangle, like this. This is the outermost circle, and the P reaches this outermost circle for the first time through a quadrangle, like this. Then P passes through 6 edges of this octagon. Again, since a single x or x bar cannot occur in the middle, so the only possibility is that x occurs in the left end, or x bar, next slide, x bar occurs in the right end. We have only 2 possibilities. Then let's look at this possibility first. X occurs in the left end. And then again after this, there are only 2 directions in which P may proceed. P follows this circle continuously, or it comes into the inner circle. In each direction, we see that a single x occurs between 2 other letters. So we can easily obtain a contradiction in this case. And what about this? Here, again, we have only 2 directions. Here and here. And if P moves into the inner circle like this, then a single x occurs between y and y bar. That's obvious contradiction. And what about this? Here, one more x occurs consecutively. That's good. But x bar occurs here. A single x bar occurs here. So we have contradiction again. And next, if x bar occurs in the right end, like this, and then, well, again, after this point, there are only 2 directions. P follows this circle continuously, like this, or P moves into the inner circle, like this. Okay? Let's look at this case first. Okay, P follows this circle continuously. Then after this point, we have two possibilities. Okay? And in either possibility, a single x occurs between 2 other letters. So we have contradiction. And what about this? This path is x actually. So if path P follows this edge x, then x occurs. Then in order to avoid a contradiction, one more x occurs should occur consecutively. So P passes through this edge. And then after this, we have only two directions because this is the outermost circle that P passes through. Only 2 directions, left side and the right side. In either case, we see that a single x bar occurs between 2 other letters. So we have contradiction. In this case as well, we can obtain a contradiction similarly. So the proof is done. So this is a proof using universe covering space, topological proof. In contrast with such topological proof, let me show you a proof using a small cancellation theory. Small cancellation theory is one of representative geometric techniques in group theory. It is used especially when every pair of cyclic permutations of relators have little cancellations in forming the product. As a matter of fact, this surface group presentation satisfies good small cancellations, such as C'1s plus epsilon, C8, and T8 conditions, which I'm going to define later. Then, it's out of question that we may think of small cancellation theory for this proof. Now let me define these small cancellation conditions. To define these small cancellation conditions, we need to assume that a given presentation, every relator is cyclically reduced, and all cyclic permutations of R and R inverse belong to a relating set R. We assume that. Then word B is called a piece if it is a common initial segment of two different elements in R, like this. Then we see that this piece B is the part to be cancelled in forming the product R sub 1 inverse R sub 2. So in small cancellation theory, small cancellation means a small piece relatively to the corresponding relator. Geometrically, this piece can be seen as a common edge between two cells with the label R sub 1 in this direction and R sub 2 in this direction. Then in our surface group case, every piece is just a one-letter word, like this. So it's only 1/8 of the whole relator. It's quite small, relatively. And then let me define a small cancellation conditions. There are three classical small cancellation conditions. The first one is a metric version, which is most commonly used. We say that the presentation satisfies condition C prime lambda if every piece has length less than lambda times the length of the corresponding relator. Then in our surface group case, every piece has length precisely 1/8 of the length of the whole relator. So this lambda should be 1/8 plus epsilon to get this inequality. And also there are two non-metric versions of small cancellation conditions, condition CP and the condition TQ. Condition CP first. If you express relator R as a product of pieces, then we need at least P pieces. In this case, we say that a presentation satisfies condition CP. And also condition TQ, for n elements in R, if there is a cancellation in each product R sub I plus 1, where the indices I are taken modulo n, then this n is at least Q. In this case, we say that the condition TQ is satisfied. Let me interpret this in terms of diagrams. By a diagram over this group presentation, we mean a finite to complex with a labeling function, which assigns label to every edge so that the boundary label of every face equals some relator. So boundary label of every face corresponds to some relator. That's the diagram. Then for condition CP, let's look at this left diagram. Here, in particular, this interior face, we have common edge here between two cells, and we know that a common edge between two cells corresponds to a piece. So we can call this piece. Then the corresponding relator of this face is expressed as a product of this many pieces here. But if condition CP is satisfied, then we need at least P pieces, which means that here we have at least P edges on the boundary. So, like this. Condition CP implies that this is the interior face. The interior face of degree is at least P. By the degree of face means by the degree of face, we mean that the number of edges on the boundary. And for condition TQ, let's look at this diagram, in particular this interior vertex. We see that there is cancellation between these two cells. Cancellation here, cancellation here, cancellation here, and cancellation here. So if condition TQ is satisfied, in order to obtain this kind of interior vertex, we need at least Q cells around, which means that the degree of this interior vertex is elastic Q. So condition TQ implies that the degree of this interior vertex is elastic Q. That's the geometric meaning of small cancellation conditions. Then there is a reason why we tend to use diagrams like that. The following theorem is a Van Kampen's theorem, which is very classical in group theory. Let me introduce this theorem. Let W be a cyclically reduced word in X, then W equals the identity in this group, if and only if there is a connected and simply connected diagram over H with a boundary label W. Proof is very simple. So let me show you its proof. First, only if direction. So suppose that W equals the identity in this group, which means that W belongs to the normal closure of R in the free group. So that W can be written as a product of conjugates of elements in R like this. Then from this product, just draw a bouquet of K balloons like this. And then assign a label a V sub 1 to this path like this, and here R sub 1 and V sub 2 R sub 2 like this. Then the boundary cycle of this diagram has label V sub 1 R sub 1 V sub 1 inverse V sub 2 R sub 2 V sub 2 inverse, etc., which is precisely equal to this product. But in order to obtain this reduced word W, we need to make cancellations. Cancellations in this product corresponds to folding in this diagram. For example, if there is a cancellation between V1 inverse and V2, then there is a common initial segment between V1 and V2. If there is a common initial segment between V1 and V2, then we may just identify those parts by folding together. In this way, we can obtain a connected and simply connected diagram with a boundary label W. So that's the on-if direction. And if direction. For if direction, suppose that there is a simply connected diagram over H. Then we want to show that the boundary label of this diagram equals the identity in this group. To prove that we use induction on the number of two cells in this diagram. The base step is obvious. Actually, the base step corresponds to the case where this diagram consists of only one cell. Then the boundary of this one cell is just a relator. That's the definition of the diagram. So that's obvious. Base step is obvious. And for inductive step, suppose that this diagram contains more than two cells. Then in that case, more than one cell, at least two cells. Then in that case, remove one cell to get to still get connected, simply connected diagram delta sub 1 like this. Then by the induction hypothesis, the boundary label of delta sub 1 equals the identity in H. And also by the definition of diagram, the label of this face equals the identity because the boundary label of this face is just some relator, which is equal to identity in group H. So this equals the identity, and the boundary cycle, this boundary cycle equals the identity. Then by performing the product, we have S sub 1, S sub 2, which is precisely the boundary cycle of whole diagram. So boundary cycle of this diagram equals the identity in group H. The proof is very simple. So due to this theorem, in order to decide whether or not a given word equals the identity in group, it suffices to consider the existence of a connected and simply connected diagram. over the group presentation with the boundary label such a word. So let's go back to our elementary proof. In the beginning, we assumed that W is a non-trivial cyclically reduced word in this set x squared yz u, such that W equals the identity in this surface group. And then by Van Kampen's theorem, which we have just seen, there is a connected and this simply connected diagram over G with a boundary label W. From the existence of this M, we would like to obtain a contradiction. In order to obtain a contradiction, any classical results are not helpful. For example, it's already known that in the case of C'(1,6) groups, any word representing the identity contains more than half of some relator. This is a well-known effect in group theory. Our surface group satisfies C'(1,8) plus epsilon, which means that our surface group is also C'(1,6) group. But this classical result does not help, because even if W here more than half, in our case, relator has length 8. So 5 letters of word corresponds to more than half. But even if W contains these 5 letters of word, Y bar, G, U, G bar, U bar, it doesn't give us any contradiction. So this classical result doesn't help. So you have to investigate further using small cancellation theory. And then we combine this inequality. It is easy to obtain this inequality. This inequality can be obtained using Euler's formula. It's easy. So combine this inequality and Euler's formula also. And as I said, this surface group presentation satisfies C8 and T8 conditions. So C8 and T8 conditions to obtain this inequality. We need some computation here. This inequality is key observation in this proof, where A denotes the number of vertices in the boundary with the degree 2, and B is the number of vertices in the boundary with the higher degree. So, applying this inequality to M doesn't give us any information, good information. So we need more technique. So actually, we have to choose an extremal disk J of M. By an extremal disk, we mean a submap which is homeomorphic to a disk, and which has a boundary cycle such that the edges occur in order in some boundary cycle of the whole map. In this example, extremal disk can be this left part and also this right part, the bright part. So this can be an extremal disk, but the middle part cannot be an extremal disk because see, this is a submap which is a homeomorphic to a disk. That's fine. But the edges on the boundary cycle of this cannot occur in order in any boundary cycle of the whole map. So this cannot be an extremal disk. So in this case, there are two extremal disks. Just to take one of extremal disk, J, and still applying the inequality to J is not enough. So we use a dual map, J star. For the dual map, actually this red map is a dual map. To construct a dual map, take the one vertex from each face, like this. And there is a common edge between two faces of J. connect this vertex and this vertex across the common edge like this. And the faces of J star is the boundary region, which is bounded by the edges of J star and which contains an interior vertex of J. So what in this case, this can be a face like that. So actually, there is a one-to-one correspondence between the interior vertices of J and the faces of J star. And also there is a one-to-one correspondence between interior face of J and the interior vertex of J star. And also we see that the degree of this face is the same as degree of this interior vertex of J, right? And the degree of this interior vertex is the same as degree of this interior face. Which means that if the original map satisfies CP and TQ conditions, its dual map satisfies CQ and TP conditions. P and Q are interchanged. But in our surface group case, both P and Q are 8. So even if we interchange P and Q, it's still C8 and T8 conditions. So this dual map J star still satisfies C8 and T8 conditions. And because we started from an extremal disk, this is connected and simply connected. And then there are 3 cases here. J star consists of a single vertex like this. If you take a J as this, then J star would consist of a single vertex like this. And case 2, J star has more than one vertices or without a vertex of degree 1 like this. If you take J, an extremal disk J as this part, then the dual map J star will look like this. So it contains more than one vertices and it doesn't have any degree 1 vertex. And in case 3, J star has a vertex of degree 1. So we have 3 obvious cases. And first case, J star consists of a single vertex just like this. Then the boundary cycle, in this case, obviously, boundary cycle of the whole map passes through all the edges of this face like this. In our case, this is actually octagon, 8 edges. So boundary cycle passes through all 8 edges, which means that a single X and the X bar should occur in between. So that's obvious contradiction. So case 1 is obvious contradiction. And case 2, well, here. J star has more than one vertices without a vertex of degree 1. While this red part is a part of J star, then to this J star we may apply this inequality. Because as I said, J star is connected and is simply connected and it satisfies C8 and T8 conditions. So we may apply this inequality to this J star. Then from this inequality, we see that there are at least 3 consecutive vertices of degree 2 on the boundary of J star. So here, well, this is a part of J star, and the 3 consecutive vertices of degree 2 like this, degree 2, degree 2, degree 2. Then from this J star, we recover G. Then we must have this kind of faces, 3 faces. Then in order to avoid a contradiction, this middle part, if you look at this middle part first, then the boundary path passes through 6 edges of this middle cell. So X occurs here, first possibility. Yes, X bar occurs in the right end here, or X occurs in top part here. Let's look at this case, for example. If X bar occurs here, then this face Well, we don't have any problem with this phase. That's good. But if you look at this phase, one more X bar occurs consecutively. That's fine. But here, a single X occurs between two different letters. So we have contradiction. Again, you see, X bar occurs here. If you look at this middle part first, in order to avoid contradiction, we assign this label, X bar. And then and top part, no problem again. And the bottom part, here, this is Z bar, which means that X bar occurs, a single X bar occurs between two letters. So we have contradiction. But remember that this is not M, this is just a J. A J is an extremal disk. So as I said, you see, J, well, for an extremal disk, we have two possibilities. The first possibility is that the extremal disk can be the whole map. And the next possibility is that it is connected to the other part at a single vertex like this. So this is just a J. If this is a whole M, then we obviously have contradiction. But if this is connected to the other part at a single vertex, then what happens? Well, suppose that such a single vertex is this vertex or this vertex. Then we cannot have a contradiction directly from this point. And then in that case, we could take 3 other consecutive vertices of degree 2. Because here in this inequality, we see that the 8 extra degree 2 vertices. So we could take 3 consecutive vertices other than this triple. So we have a contradiction in case 2. And in case 3, we need the mole technique. If a J star has degree 1 vertex, then we need to remove all degree 1 vertices together with the edges attached to them. Call it J star minus S. Then the first possibility is that J star minus S is empty, or it consists of a single vertex. It's easy to prove this case. And next case, J star minus S has a vertex of degree 1. This case is easy as well. And the final case, J star minus has more than 1 vertices with a degree 1 vertex. So while J star minus S has no degree 1 vertex, and then in this case, we may apply the inequality, the previous inequality, to this J star minus S. Then we have 3 consecutive vertices of degree 2 in J star minus S, like this. Then from this, recover a J, like this. Then in order to obtain a contradiction, we can think of this possibility. Well, there might be a vertex of degree 1 like this, because this is a J star minus S. So we already removed the degree 1 vertex attached to together with the edges. So if you recover J star, then it might be some edge attached to this vertex like this. Then even if a single X bar occurs here, we don't have any contradiction. But if you read this boundary cycle, then a single X occurs in the middle. So we still have a contradiction. So in any case, we have a contradiction. So proof is done. This is, I think, this is a good proof using small cancellation theory. Good example to use small cancellation theory. And now let me introduce my recent results. Recently, Makoto Sakuma and I obtained some results about two-bridge link groups and the even heckoid groups. There is a geometric interpretation of these groups. But for now, let me just introduce these groups in terms of group presentations like this. Two-bridge link groups are parameterized by extended rational number, and the even heckoid groups are parameterized by extended rational number and the positive integer greater than 1. Both these groups have presentations with two generators and a single layer. And there is a known formula to find this single layer as follows. If R equals infinity, then U sub R actually the empty word, which means that the corresponding two-bridge link group is a free group of rank 2. Otherwise, R is a rational number. So we may express R as Q over P, where P and Q are relatively prime integers with Q positive, with P positive. Then if P is odd, we use this formula to get U sub R. And if P is even, we use this formula to get U sub R. Then for example, two-bridge link group associating with the rational number 3 over 7 has this presentation. To get this single layer, we applied this formula. This is P odd case, we applied this formula. And also heckoid group, even heckoid group with rational numbers 3 over 7 and n equals 2 has this presentation. A single layer is the square of this single layer like this. And the initial point of our research was the observation that this two-bridge link group satisfies C4 and the T4 small cancellation conditions. Before talking about the results, let me talk about the geometric interpretations of two-bridge link groups and the even heckoid groups. Two-bridge link groups are just fundamental groups of two-bridge link complements in 3 spheres. And the even heckoid groups are fundamental groups of even heckoid groups are the fundamental groups of even heckoid all B4s. Two-bridge link complement in 3 spheres is manifold, but even heckoid all B4 is just all B4, not manifold. Both of these are 3-dimensional, so 3-dimensional manifold and 3-dimensional all B4. And then what is a two-bridge link? Well, two-bridge links are parameterized by extended rational number R. Then by Schubert's classification on two-bridge links, we may assume that this rational number R, extended rational number R, is infinity or R lies in this interval. If R equals infinity, the corresponding two-bridge link is just a trivial link with the 2 components. And if R lies in this interval, since R is a rational number, we may express R in terms of continued fraction like this. For example, let's look at this example. 5 over 17 has this continued fraction expansion. Then from this expansion, we see that we have that 3, 2, 2, 3, 2, 2 like this. Then to get the corresponding two-bridge links, starting with the trivial 2 tangles, make 3 half twists from this first number 3, and from the second number 2, make negative 2 half twists, and from this last 2, make 2 half twists here. So we can have a two-bridge link in this way. Then we can obviously consider a two-bridge link complement in 3 spheres, and the fundamental group of such a complement is a two-bridge link group. And also even heckoid all B4. What is even heckoid all B4? This is even heckoid all B4 actually. and it has the same complement as a two-bridge link, but it has a singularity of index n at the bottom. That's the difference. This is the Olby fold. Then the following question naturally arises. Which essential simple loops are non-homotopic in two-bridge link complement? And which essential simple loops are non-homotopic in even Hecoid Olby fold? That's the natural question to understand the three-dimensional manifold and the Olby fold. This right picture shows that this simple loop is actually non-homotopic in this link complement. And this is a two-bridge link. We see that if you take this loop lower, then we get this, right? And take this lower further, then we get this. This is obviously a non-homotopic in this link complement. So like this, we wanted to find all essential simple loops which are non-homotopic in a two-bridge link complement, and in an even Hecoid Olby fold as well. This question is equivalent to saying that which essential simple loops represent the identity word, identity element in a two-bridge link group or in even Hecoid group. So we obtained a complete answer to this question using small cancellation theory, applied to two-bridge link groups and the even Hecoid groups. And as Kleinian groups, two-bridge link groups and the Hecoid groups form a special class of Kleinian groups. Let me talk about it. Discrete subgroup of PSL2C, which is the isometry orientation preserving isometry group of H cube, is called a Kleinian group. Then a three-dimensional Olby fold is said to be hyperbolic if it is homeomorphic to a quotient space of H cube by some Kleinian group. In particular, if this Kleinian group is torsion-free, then this Olby fold becomes manifold. And also there are three classes of elements in a Kleinian group called parabolic, elliptic, and loxodromic, according to their traces. In particular, if the trace equals plus minus 2, we call such an element parabolic. Then we are interested in Kleinian groups which are generated by two parabolic transformations. Well, actually, by some computation, you can see that every such group is conjugate to G sub omega, which is generated by these two parabolic transformations. So up to conjugation, every two parabolic generator Kleinian group is G sub omega, which has a single complex parameter W. So we want to see for which omega G sub omega is a free group. There is a good answer for that question. As a matter of fact, if omega, complex number omega, this is part of complex plane. If omega belongs to this colored region, then the corresponding G sub omega becomes a free group. But we are interested in a non-free G sub omega. A complete classification of non-free G sub omega is announced by Ago and proved by Sakuma as follows. If G sub omega is torsion-free, then it is a two-bridge link group. And if it's not torsion-free, then it's a Hecoid group. Which means that every non-free G sub omega is either two-bridge link group or a Hecoid group. Then the omega which corresponds to two-bridge link group or heckoid group is plotted here like this. Actually, those points are plotted on these rays. And the ending point corresponds to two-bridge link group. And the other parts on the same ray corresponds to heckoid group with the same rational number. For example, this is this omega corresponds to two-bridge link group. This ending point corresponds to two-bridge link group with associating with the rational number 2/5. Then on this ray, the other points correspond to heckoid group with the same rational numbers 2/5. And as n gets bigger and bigger, the corresponding points gets closer and closer to this free region. Well, it makes sense because this is two-bridge link group presentation, which I already introduced, and the even heckoid group has this presentation, if you remember. And the other heckoid group, this is a presentation of other heckoid group. Then we see that this number corresponds to n. So in even case, n is just integer, but in odd case, n is a half integer, but not an integer. In this case, we see that as n gets bigger and bigger, the length of this ladder gets longer and longer, which means that this group gets closer and closer to free group. Well, anyway, for this reason, by studying two-bridge link groups and the heckoid groups, we want to find geometric properties of hyperbolic orbifolds whose hyperbolic structures are determined by non-free G sub omega. That was our goal. But unfortunately, as you see here, other heckoid group has 3 layers, and this presentation doesn't satisfy any good small cancellation conditions. So for now, we don't have any good idea how to treat this other heckoid group. But the two-bridge link group and the even heckoid groups have good small cancellation conditions. So we completely proved for these groups and obtained nice results. There is a reason why we name these groups heckoid groups. Well, as a matter of fact, these groups can be seen as a generalization of Hecke groups, classical Hecke groups. Let me remind you the definition of classical Hecke groups. Hecke groups are Kleinian groups generated by these two transformations. Here, lambda q equals 2 times cosine pi over q, and the q equals 3, 4, etc. So Hecke groups are parameterized by positive integers bigger than 2, like this. In particular, if q equals 3, then lambda 3 becomes 1. In that case, Hecke group is a modular group. So Hecke group is a generalization of modular group. And then by computation, we can see that if Q is odd, like this, then it is precisely two parabolic generator Kleinian groups. And also which is isomorphic to heckoid group with the rational number r equals 1 and this so other heckoid group. And also if Q equals even like this, unfortunately Hecke group is not a two parabolic generator Kleinian group, but instead it contains two parabolic generator subgroups as maximal subgroups. And such a maximal subgroup is actually this even heckoid group. So we can say that the maximal to parabolic generator subgroups of Hecke groups are the simplest Heckoid groups, which are the Heckoid groups for the trivial knot. So in this viewpoint, we can say that the Heckoid groups are a generalization of Hecke groups. This is the reason why we name these groups Heckoid groups. So, now let me introduce our results about two-region link groups. We obtained these results using small cancellation theory. We first observed that this presentation satisfies C4 and T4 conditions. And using small cancellation theory, we proved the following fact. Briefly speaking, if this U sub S represents essential simple loop, if U sub S equals the identity in this two-region link group, then such a word contains some particular part of this later. We explicitly described this particular part. Well, actually, for example, in this case, in this two-region link group, such a particular part corresponds to this. If U sub S equals the identity, the U sub S must contain this part or this part as a subword. And by this observation, we obtained the following complete answer to the question that which essential simple loops are null homotopy in two-region link coupling. This is a complete answer to that question. See, U sub S equals 1 in this two-region link group, if and only if this rational number S has this form. As a matter of fact, every essential simple loop has a unique slope. So this S represents the slope of the essential simple loop. So for example, if R equals 2 over 7, if you express 2 over 7 as a continued fraction expansion, you get 3, 2. And this rational number, 69 over 238, if you express this as continued fraction expansion, then you get 3, 2, 4, 2, 3. Then 3, 2 comes from this R, and 4 even number, here we need even number, and the opposite, the inverse of this. So the 3, 2, the inverse of this, 2, 3, like this. So this S satisfies this form. Then according to this theorem, we say that the essential simple loop of this slope is null homotopic in two-region link associating with this rational number 2 over 7. That's an example of our result. Furthermore, we found that we obtained the complete answer to the question that which two essential simple loops are homotopic to each other in two-region link groups. But it's too complicated, so let me just skip it. And now this is the result about even Heckoid groups. And again, we observed that this Heckoid group presentation satisfies C4N and T4 small cancellation conditions. And using small cancellation theory, we proved this part. Just like before, if U sub S equals 1 in this Heckoid group, in even Heckoid group, such a word contains some particular part of this layer. In this example, such a particular part corresponds to this. So if U sub S equals 1 in this Heckoid group, then it must contain this part or this part as a subword. From this observation, we were able to prove this theorem, which gives a complete answer to the question. That U sub S equals 1 in this Heckoid group if and only if this rational number S has this form. And in this case as well, we completely found that found the answer to the question that which two essential simple loops are homotopic to each other in this Heckoid all be false. using small cancellation theory again. So this is it. Thank you.